The Newtons and friends were taking tea beneath the boughs of an apple tree when a falling fruit landed on the head of the family. Mrs. Newton cried, "Well, dearie me, that could have caused an injury." But clever Isaac alone could see the situation's true gravity. All right. I did not write that poem, although it's kind of funny, isn't it? So, all right. Apologies for being a little late. This is, if you guys have been keeping up, I've been on vacation for the last 2 weeks, and today is my first day back in terms of getting back to the show. So, SG2 on Space, the only weekly space show, except when I'm on vacation, clearly. Go on facebook.com/The Shen Show. Please support the show. Patreon.com/SG2 on Space. And without further ado, let me introduce Dr. Leonard Kramer over there. How are you doing?
Just fine. Better than I deserve.
All right. That's great to hear. So
I got all my steps in already today.
Oh, you did? Okay.
Yeah.
So you can just sit there then, right? So that's great.
Yeah.
I was gonna say we were meaning to talk about this a little while back, but I figured we're talking about the Cavendish Experiment today.
Mm-hmm.
You brought that up a few weeks ago. So what exactly is that? I gave a poem about gravity, and so how is this related, and what is it?
Well, I mean, yeah, it's a measure. It's a terrestrial laboratory measurement of the attraction between massive bodies, and what's remarkable about it is it's an 18th century phenomenon, or it was done in the 18th century by a guy named Cavendish, and he was in his 70s at the time, if I read that right, and so it's like a marvel of like, I mean, you know that you're attracted to the Earth, right? Because we're walking around, so we know about gravity, and at that time they knew about Newton. You know, and they believe that they believe this force. There you see this inverse square force.
Did they, Leonard, sorry to interrupt you. So
yeah,
Newton's universal law of gravitation for every viewer's reference. Force equals gravitational constant times the mass of object 1 times the mass of object 2 divided by r squared, where r is the distance between the center of the masses of these two objects. So let me ask you this. So they believed in this formula. The only big constant there, the universal constant, so to speak, is G, the big G. Did they know that?
They did not know that. They knew G times M1, where M is the mass of the Earth. Okay, they knew that from astronomical calculations, but they did not know. They did not know the universal gravity constant. Cavendish was not after that specifically. I think the challenge was to determine the mass of the Earth, or the way his paper reads, the density of the Earth, which is essentially the same thing. And so it's a challenge. And so the way he went about it was, here, put the slide back up. I'm sorry, I didn't mean to. I was going to still talk to the slide. If you can. Can you get it up?
All right.
There it is. Okay, so you know, the way he did that was he actually had two massive bodies, you know, two heavy bodies, and through a very delicate experiment, which is, it's remarkable, you know, in 1797 to 1798, over the period of about a year, I think he was working on trying to refine this experimental measurement. He actually inherited the idea and the device from someone else who died. It wasn't a relative, but it was somebody that he was interested in pursuing this experiment. And the way they did it was they had these two masses that were on a beam balance, and then he brought two other masses close to it, and was able to observe the deflection of the beam with on a suspended fiber in the middle. And he used a small telescope to view it. There it is. So here's a kind of a modern version of it. It was a light source, and then a mirror, and then he had to get I think he put it in like a shack or inside of an isolated area to keep the air currents away from it. In the paper, he talks about, how sensitive it is to just air currents. And this experiment has been repeated probably tens of thousands of times over the years, even in like it can be done in the high school laboratory and so forth. And so he was able to actually directly measure the force that would turn that fiber, and then he could back out because he knew the mass of the two masses, and so and the distance between them, and so he could figure out effectively he figured out the universal gravitational constant. And so it's I don't know, it's just a very interesting fact that he was able to do this. People don't have the usual notion. I mean, you hear this all the time. Well, objects attract each other, but I think a lot of people don't know that it's an actual thing that you can measure in the laboratory. The force of attraction between these two bodies is about 1/50,000,000th of the force of the weight of the objects. So their attraction for each other is diminished in that, by that amount. Some other things that go with this have to do with the dimensions of the solar system. A lot of people, I guess the thing that I like about all of this is that, people today like to walk around and say that they know things. Like, I know the Earth, I know the Earth is round, or I know the Earth rotates around the sun, revolves around the sun. But
yeah,
how do you know it? Do you really know it, or do you know what someone told you about it? And if you went about trying to prove it, how would you go about that? And I think the overwhelming majority of people would go, well, I'd go on Google and
well,
but they didn't have this, and so they were actually interested in checking these things on their own. The dimension of the solar system, even how far away the sun is a challenge. It's not completely obvious how to determine the dimensions of the solar system, and it's sort of related to this because the force of the attraction of the planets around the sun were well known. They weighed the sun before they had the masses of any of the planets, based upon the periods of an orbit. So, you got a video to show?
Well, I figured this is, you're saying how people have done this numerous times. This is an example of this physics teacher, I believe, setting up a very, by the way, this setup is so simple that anybody could do it. Like, you could set it up at home. Just take 2 bowling balls. You see the string hanging down, right?
Mm-hmm.
And the mass is on there. Now, you do have to be careful, like, yeah, you can see the time is moving. This is obviously fast forwarded, like, and they have that light. You see that light?
Yeah. So the whole issue, and this is what Cavendish mentioned.
Quietly in the corner, trying not to screw anything up. So let's see where we're at with this. I'll give you guys the benefit of the high speed again, and I'll make a few more markings. We'll see where our new center is and how it compares to the old center.
This might be kind of boring.
Yeah.
Really, my interactions have caused a bigger swing back and forth. But it
also I was going to say, I don't.
So we'll make some measurements in just a minute to verify that. But it looks like we have caused some kind of a
let's end the video.
Including those bowling.
If you guys want to watch the whole video, it's going to take
about. So we've seen a few more swings back and forth.
9 minutes. So just end it. But you can see that, by doing some simple experiments, I agree with you, Leonard. Like, a lot of the stuff we do take for granted. Like, when I took physics, they just said this is G, all right, and just formula. So there was no experiment done to verify or anything.
and it's kind of valuable to know those things. Humanity, the ancient Greeks knew how big the Earth was to within 5%. And how did they do that? They didn't have rockets to go up and look at the Earth or anything. How did they do that? I guess we could talk about that sometime. But they knew how far away they didn't know how far away the sun was, but that was determined in the 17th century from Venus. They used the planet Venus, and I think probably Mercury also, that to transit the sun, and then the time of transit measured from distant points on the Earth could tell you something about the dimensions of the Earth's orbit. In other words, you can figure that out. So there's all kinds of stuff like that. That's curious. Curious people who want to think of themselves as intelligent and smart.
Well, Leonard, I mean, have you done these experiments before? Out of curiosity.
No, I haven't. No, I haven't. I have seen Cavendish's experiment. But that's fair. I mean, but I don't know. It's like I see people talking about, for example, like the flat earthers, and I don't want to talk about flat Earth. Okay, I don't want to talk about it. Okay, but the anti-flat earthers to me are just as annoying as the flat earthers. In fact, I've never interacted with a flat earther, but I've interacted with lots of anti-flat earthers, and I just find it like, why are you wasting my life with this? I don't. Why are you wasting your life?
Anti-flat earthers are those who argue against flat earthers. Is that what you're
saying? Right.
Okay.
It's like, how do you know the Earth is flat? I mean, how do you know the Earth is round? How do you know the Earth rotates around the sun? I don't think that they actually have they don't have a good, clear idea about that. They wouldn't know how to measure
let me think about it. I think how I would do it is look at, I guess I would need to look at the astronomical observations, right? Which you can see every night or every day. And then I would create a model. I could code up a model where, let's just say, somehow Earth is the center of the world, of the solar system. It's revolving around the Earth. And then see how well that fits my data versus the reality, which is Earth going around the sun.
Yeah. So the Earth being fixed and the stars going around it,
right,
actually fits that model very well. In fact, one of the objections to the idea that the Earth moves around in the orbit is that there was no way in the 15th century, 16th, in Galileo's time, there was no way to measure parallax of stars. And so that was one of the objections that was brought up was, well, if the sun is moving from one side of the solar system to the other side of the solar system, why don't we see some apparent motion of the stars? And I think it's actually a good question, right? So anyway,
I think that's something we should bring up next time, because that is interesting on how we proved that fact as well, right? So,
all of those things, things that were known in ancient times, like the circumference of the Earth, and various various kinds of things like that, especially that are interesting.
The circumference of the Earth, that I recall, we can do it with the shadows, right? At different levels.
Yeah.
That was really interesting. How you can do that.
They calculated pi also. They were able to calculate pi out to, I think, 5 digits. And I don't know how to do that.
What? Surely you know how to. Yeah.
Not to I think 6 digits. I think one of the Greek.
I mean, even like Yeah, it's I don't know how far the Egyptians and the Babylonians and the Sumerians and whatever before them, like everybody seemed to know pi, but it's just how accurate you were, right? So how you did
Right.
it.
Well, actually, because the Greeks were very they saw the universe as ordered and perfect, and so it was extremely annoying that pi is not, for example, 3.
Right,
It's 3.14159, and you can look up all the rest of the digits and keep.
Well,
But it's a not repeating decimal, and I think that was very, very annoying to them. And the assumption that the orbits of the planets were perfect circles and so forth were mistakes they were making.
right. So we're gonna have to move on to one of my favorite topics. What do you think that is?
Animal husbandry. Weren't you saying something
All right,
about
animal husbandry.
you were breeding donkeys?
Actually, no. I'm talking about
No.
UFOs.
Oh,
So,
UFOs, of course, yeah.
this is supposedly possible UFOs videotape near Indiana Airport. This was on November 17th, I believe. Let's take a look.
It's very compelling. Yeah.
Okay,
Wow.
so from what I see, I really don't notice much. What is happening?
Yeah, I wouldn't be able to tell, really what that is. It looks like it might be just like a light source inside a dark room.
This person. So here's what this person said. I've been seeing some strange stuff up in the sky, but I've never had the opportunity to actually get it on video. I've been outside almost every clear night for the last year and a half, so I've seen everything you could think of when it comes to space objects, including rockets, shooting stars, satellites, comets, planes, etc. You name it, I've seen it. That night, I went to look out my window because I love the constellation Orion because of nebula, and I see these two very big and completely stationary balls of light, and I'm sitting there for like 30 seconds because I am so mesmerized. I've lived here for 16, maybe almost 17 years. I've never seen anything like what I've been seeing in my entire life, and I'm glad I finally caught it on video. Except the video is really hard to see anything.
It's very hard to. It's not that compelling.
You don't think it's compelling? Okay.
No, I mean, the testimony is. The testimony sounds believable, but the video, I can't tell anything about it.
Isn't what you say is that they're using some alien blurring technology?
Yeah, that could be one explanation, that the aliens have video blurring capability, so that no matter how sharply in focus you make it, it shows up blurry and distant and indistinct.
Yeah.
Bigfoot has that. Bigfoot has that technology also. So Bigfoot may be.
You might have
alien.
seen videos like this before, but here's the big secret.
Yeah, no,
Anyone can make one of these videos in a few.
Okay. That was strange, but I agree. Leonard, in this case, it's really not very compelling. I don't know what it is, but for all you know, it's just too. Yeah. But do you have anything more interesting to add? Since we're trying to.
You mean about UFOs?
No, in general.
You don't want me to say. You don't. Well, in general. In
general, about today's topic, let's just say.
Well, gravity is a very important component of a controlling force of the universe. It's really, here's one thing. The Big Bang. People say the Big Bang. There's the energy for the Big Bang comes at the expense of gravity. So actually, all of the gravity in the universe is negative. It constitutes negative energy. I'm not saying like I'm not making a woo-woo kind of statement. I'm saying that relative to all of the other energy, it's sort of create. The universe was created. It looks like the universe was created with equal amounts of gravitational and sensible energy, and that they're equal and opposite, and that the Big Bang seems to be some kind of process that separated those two events.
That is.
And so it's free. It's free. I mean, the energy didn't come from anywhere. The energy's still there. It's just at the expense of the gravitational energy.
We should talk about that next time. I also need to add the exciting news that you probably know is that the James Webb Space Telescope is launching in less than 2 weeks.
Yeah.
So.
Yeah, I hope so. I hope it's okay. I'm really not very confident. I heard something on the news the other day where a manager was saying we are 100% certain that we will be successful. He used the word 100%, and that really deflated me.
Well, it's better than saying we have 50%. You might as well
No, because if you say 100%, then that means that you're just trying to cover up for some uncertainties that you actually have, and so that the thing is so complicated that I don't know. I hope, because it will be revolutionary. But anyway, we're out of time.
Yes, likewise. All right. So thank you everybody for watching the show. Live every Wednesday night, 6:30.
Yep. Thank you.
Out of town. This has been SG2 on Space, which you can find on Facebook.com/ thank you for the commentary, Leonard. Facebook.com/The Shen Show. Support Patreon.com/SG2 on Space. And the catchphrase is
keep looking up, because you never know what you will see.
That's right. Look up.
I've been practicing.
You never know what you will see. Mm-hmm. Yes, that's right. So with that, everybody, namaste.
Good night. Oh, lovely.